Hi, and thank you very much for the opportunity to present my research today. My name is Maximilian Günther, and I'm currently a Torres Postdoctoral Fellow at MIT. In the next 5 minutes, I will highlight our study of stellar flares and potentially habitable worlds, searching over 200,000 stars across the entire sky with the Transiting Exoplanet Survey Satellite, or TESS. Even our nearest neighbor, Proxima Centauri, has an Earth-sized exoplanet with a temperature that might just be right for life. But Proxima Centauri is a red dwarf, only about 15% the size of the Sun and half its temperature. Red dwarfs have become such a prime focus for us because they make up 70% of all stars and on average host at least one Earth-sized exoplanet, often multiple. Additionally, their small sizes and low temperatures mean that we can detect and characterize exoplanets around them much easier. And best of all, since our methods are biased towards exoplanets in short orbits, these cool stars actually place them into temperate regions where liquid water might be possible. However, as we all know, for habitability there are many other major factors to consider. The one I'm focusing on? Stellar flares. These immense brightening events emit radiation from X-rays to the optical. And they're often accompanied by coronal mass ejections, streams of charged particles that get thrown out into space. Together, they release energies of up to 10 to the 38 erg, which equals millions of nuclear bombs at once. These violent stellar outbursts drastically shape the exoplanets around them, especially if they're on weakly orbits. Stellar flares and coronal mass ejections can interfere with the exoplanet's atmospheric chemistry, or even completely strip off these atmospheres. On the other hand, flares might actually be what initiates life in the first place, by triggering UV prebiotic chemistry. What fascinates me is understanding where this fine, sweet spot of enough but not too much flaring lies. This is where our TESS Space Telescope study comes in. Over the past 2 years, we surveyed almost the entire sky, taking pictures every 2 minutes of over 200,000 stars. Zooming into this large composite image here and picking a certain star, we see how its light spreads out on our image pixels. However, that yellow blob that you see here, this is just a neighboring star. The star I want to draw your attention to is marked in this white outline and barely visible by eye right now. But let's see what happens if we look at this again in about 1 hour. We suddenly have an immense brightening of this star. And continuing to take pictures, let's see how this develops after about 5 hours. It's all gone again. The star is back to its quiescent brightness. If we look at the whole light curve, we see that this red dwarf got brighter by a factor of 16. We can't even imagine anything like that for our Sun. Human eyes are exceptionally good at picking out flares. But in the big data era of TESS and similar missions, human inspection would take a lifetime. That is why we developed and employed Bayesian frameworks and neural networks to do this task much more efficiently and robustly. In particular, I want to highlight Alice Fitter and Adina Feinstein's stellar network here. And despite all the intrinsic variability of red dwarfs, we can even pick out the smallest flares robustly and even assign them probabilities as to how much we trust them. The Kepler mission had allowed us a large ensemble study of stellar flares. And this diagram is showing the effective temperature of these stars on the x-axis versus the test band magnitude on the y-axis for all the flaring stars catalogued by Kepler. In our first test study, based on only sectors 1 and 2, we could already explore a completely new parameter space, a large ensemble of flaring red dwarfs. Now, adding all data from TESS year 1 and 2 into this, we see how drastically we can expand this. And this is if we only trust the really high probability flares. If we include lower probability signals, we increase it even more. But what do we learn from this large ensemble about the physics of flares and their link to life? Enter the flare frequency diagram, which is a cumulative distribution histogram. The x-axis shows a given threshold energy, while the y-axis shows how many flares above that energy we observe on average per day. For example, we have a big flare with an energy of 10 to the 35.5 erg once every few weeks. Now, our Sun also has flares, but on a drastically different scale. Even the largest solar flare ever recorded, the Carrington event from 1859, only reached an energy of 10 to the 33.5 erg. If you guide your eye vertically on this plot, you see that flares like the Carrington event occur once every few days on this particular red dwarf. Now, what about other red dwarfs? All of them are much more active than our Sun. But also, there is an intrinsic spread among them. By approximating the flaring events as power laws, we can extrapolate into unobserved regimes. And this allows us to finally link them to criteria for life. The red area highlights where flares and coronal mass ejections could dissociate the ozone in a planetary atmosphere. As ozone is the primary absorbent for harmful radiation, the next stellar outburst could penetrate through and sterilize all surface biology. The green area, on the other hand, highlights that life needs an energy source to originate. While this could be lightning strikes or hydrothermal vents, my collaborators found that it most likely comes from stellar UV light. However, red dwarfs alone have too little UV radiation to trigger this. But their stellar flares are the perfect UV delivery. Thank you very much for the opportunity to present my research today.